So we're going to start off our conversation of quadratic polynomials kind of at the obvious place by talking about what one is. So a quadratic polynomial is one that can be written in this form, ax squared plus bx plus c, where a, b, and c are any real number except that one extra restriction that a can't be 0. In other words, it's a second degree polynomial. Now, when I see something like this a not equal to 0 restriction, partly because this is how mathematicians think and partly because I'm a little ornery sometimes, my first thought is, oh really? So what would happen if I let it be equal to 0? Well, if you substitute 0 for the a in the x squared term, that whole term is going to go away. You're going to be left with just bx plus c, which is just a linear expression, a first-degree polynomial, which is a very different thing from what we want to talk about when we're talking about quadratic ones. So let's look at some examples here. This expression is a quadratic polynomial. It's a pretty well-behaved one where the coefficients are just natural numbers. This one is also a quadratic polynomial, even though the coefficients aren't quite as nice, if you will. And finally, this very simple one also meets the definition if we let b and c both equal 0. Okay, so how about this one? At first glance, it doesn't seem to fit the bill because of that x cubed term. But remember that the definition just says can be written in the form. This kind of expression is why that phrase is in the definition. If we simplify this by canceling out the two x cubed terms, the expression simplifies to this, and yeah, this does meet the definition. Now, you have to be careful about taking that idea of simplifying too far. Right? Take this expression, for example. You might be tempted to cancel out those x minus 1s, which would leave you with what, x squared plus 3x, which seems to look good, but there's a problem. The original expression here isn't defined when x equals 1, where the simplified version, x squared plus 3x, would be. So, strictly speaking, and mathematicians like to be strict about these things, the two expressions wouldn't be equal to each other everywhere, so we couldn't say that this expression simplifies to a polynomial of any kind, quadratic or otherwise. So what does the graph of a quadratic function look like? Well, that's a great question. We're going to spend some time looking at that in some detail. But for now, that whole later conversation is going to start from this very basic polynomial, y equals x squared. Now, really kind of deriving in full mathematical splendor what the graph looks like requires some things that are a little bit beyond us. We need to start by proving that by showing that it's continuous. Then we're going to talk about its end behavior. Then we can use some calculus techniques to find the maximum and minimum values. More than we're going to do at this point in the process. For our purposes, plotting some points will be sufficient. Right? And if you pick some x values, positive and negative, calculate the corresponding y values, plot those, and just kind of draw the smooth curve through them, you'll get something like this. This is what Excel gives me. Right? I just calculated some points, handed them to Excel, said, show me the graph through them. And it came up with this. And this is fine. This gives us the idea. We can see where the low point is, and we can see the general U shape that all quadratic functions, all quadratic polynomials have. But it's a little deceptive. When Excel does these graphs, it tries to kind of fit everything in a way that is, to its mind, visually pleasing. And the problem with that is if you look at the two axes, the distance from 0 to 1 on the x-axis looks like almost twice, maybe more than twice, the distance from 0 to 1 on the y-axis. And that's a problem. Because the axes aren't to the same scale, you're getting a good idea of the general shape, but the graph is going to be distorted. All right, so what I did is I took this graph and I adjusted it. I stretched it horizontally until the scales were the same. right? And when I did that, I got a graph that looks something like this. Now, again, very similar, right? The same basic shape. But from my properly scaled graph, I think you get a better idea of the speed. You get a better idea for exactly how fast this quadratic function is increasing. So either way, really, for our purposes going forward, talking about some more complicated graphs, more complicated quadratic functions, ones with x terms and constants and so forth. Really, in your mind, just be aware the graph of a quadratic function has this kind of U shape. So looking ahead to the next lecture, we're going to pick up where we left off here with those graphs and see how we can extend that to some more interesting quadratic polynomials using the idea of transformations. Right? Those are going to be a key tool in a lot of the graphing exercises that you'll do. Not only we're talking about quadratic equations, but other things like logarithms and exponents and all sorts of other functions that you'll talk about as you go along here.